This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss some technology solutions and problem extensions for the 2019 AP Calculus exam free response question BC2. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the free response question and then the scoring guidelines used at the AP Calculus reading in Kansas City. And I'll highlight the solutions presented in these guidelines, emphasizing the step or the expression necessary to earn each point. I'll present the solution to each problem in a little greater detail with more explanation than given in the scoring guidelines. This was a calculator active question, so I'll show you how to use technology to explore and answer parts of this question and to confirm solutions where appropriate. And I'll also suggest a few problem extensions. These are additional AP Calculus type questions that involve some of the concepts associated with this question. This free response question involves a polar curve, r of theta equal to 3 times the square root of theta, sine of theta squared, for theta between 0 and the square root of pi. The graph of this polar curve is shown in the figure, and S is the region bounded by or enclosed by this curve. In Part A, we need to find the area of the region S. In Part B, we need to find the average distance from the origin to a point on the polar curve, for theta between 0 and the square root of pi. In Part C, we're told that there is a line through the origin with slope m that divides the region S into two regions of equal area. And we're asked to write an equation whose solution yields the value of m. And finally, in Part D, A of k is defined to be the area of that portion of S that lies inside the circle r equal k times the cosine of theta. And we need to find the limit as k goes to infinity of A of k. Part A was worth 2 points. The first point was for writing a correct integral that can be used to find the area of the region S. Now this includes the bounds 0 and the square root of pi, but does not include the constant or the coefficient in front, 1/2. The second point was for the answer, and that means including the 1/2 in front and for using technology to find the area. Now, the answer here is written with 6 places to the right of the decimal, but the student must only report 3 places to the right of the decimal, rounded or truncated. And in this case, that's the same value, 3.534. When scoring the exams, all extra digits to the right are ignored. Part B was also worth 2 points, and it was scored in a similar manner. The first point was for the integral, including the bounds. And the second point was for the answer, and again, the constant in front was part of the answer point. This answer rounds to 1.58, and the student can present this answer with or without the trailing 0, and it truncates to 1.579. Part C was worth 3 points, and it's a little tricky to isolate these points on the scoring standard. The first point was for writing an expression that equates two polar areas. Now this means we must see a structurally correct equation involving at least one polar area integral. And structurally correct means that the student has conveyed a polar integral equal to 1/2 the area found in Part A. The second point in Part C was for using an inverse trig function applied to m as a limit of integration. To earn this point, there must be an integral with limits that are 2 angles, and one limit must involve an inverse trig function that somehow incorporates m. Now this point can be earned even if the integral does not represent area. The third point in Part C was for putting the first 2 conceptual ideas together and for presenting a correct equation. So all 3 points are here in this expression: equating polar areas, one limit involves an inverse trig function, and darn it, it's the correct equation. Part D was worth 2 points. The first point was for using the correct limits of integration, 0 and pi over 2. It was okay to use 1.571 for this point, but using this approximation does not yield the correct final answer. However, this does demonstrate a conceptual understanding of the limit process. That is, as k increases without bound, then the circle r equal k times the cosine of theta will eventually contain the portion of the region S in quadrant 1. The second point in Part D was for the answer, with a supporting integral. And it was okay here to use r of theta instead of writing out the actual expression. Let's take a closer look at the solutions, and where appropriate, the use of technology to answer these questions. In Part A, we need to find the area of the region bounded by a polar curve between theta equals 0 and theta equal the square root of pi. Using the formula for area of a polar region, we need to find 1/2 the integral from 0 to the square root of pi of r of theta squared. Since this is a calculator active question, I'll use the TI-Nspire to find this answer. So first, I defined the function r. I started with 1/2 and then I used the definite integral template, filled in the bounds and the integrand, and found the area. Note that the TI-Nspire CAS version returns an exact symbolic answer, which is really cool. And this, of course, earned the answer point. I wonder if you can do this by hand. Well, here's the numerical answer, which I found by simply multiplying the symbolic answer by 1, well, a 1 with a decimal point. And using my calculator, here's a graph of the polar curve for theta between 0 and the square root of pi. Notice that the curve doesn't quite connect at the origin. You might think about why this happens, and how you might change certain settings to produce a slightly better graph. Here's an example for you to try. So let's consider the polar curve given in this free response question. First, if it's possible, sketch a graph of the complete polar curve. If it's not possible, explain why. Okay, and maybe you can explain what happens in general to this graph as theta increases. In Part B, let r sub 1 be the region bounded by the polar curve for theta between the square root of pi and the square root of 2 pi. Find the area of r sub 1 and sketch a graph to illustrate this result. In Part C, do the same thing for this region r sub 2. And in Part D, use all of these results and the free response question to see if you can find the pattern here. I think this is actually a pretty amazing result. In Part B, we need to find an average value, the average distance from the origin to a point on the polar curve. Well, the distance from the origin is simply the expression r of theta. So we need to find the average value of r of theta over the interval 0 to the square root of pi. Now here's how I found this using technology. It's interesting that the TI-Nspire did not return a symbolic answer here. You might think about why. Here's another way to think about and solve this problem. We know that the distance from any point x, y in the plane to the origin is given by the square root of x squared plus y squared. So I'm going to start by writing x and y in terms of r and theta. So I'm using the equations that relate rectangular coordinates to polar coordinates. Now find the average distance from the origin, substituting for x and y. And here's the result using technology. And we got 1.580 again, thank goodness. Here's another example for you to try. Since many students tried to find an arc length in this problem, I think we should probably find one. So let's consider the same polar curve. Find the length of the polar curve for theta between 0 and the square root of pi, and then for theta between the square root of pi and the square root of 2 pi. And you might also think about the arc length of more segments or loops like this. Next, of course, would be the square root of 2 pi to the square root of 3 pi, and so forth. I wonder if there's a limit here. In Part C, it seems reasonable that there is a line through the origin with positive slope m that divides the region S into two regions with equal areas. So we need to write an equation whose solution yields the value of m. I think intuitively we need to use half the area of the region S found in Part A. And since we're working with a polar curve and therefore polar area, we need to convert the equation for the line, given in terms of x and y, into one involving theta and r. We know that the tangent of theta is equal to y over x, which is m in this case. So solving for theta, we have that theta is equal to the tangent inverse of m. And here's a figure to illustrate this problem. So the area of the region bounded by the lines theta equals 0 to theta equal to the tangent inverse of m must be equal to 1/2 the area found in Part A. And here's the mathematical translation. And here's a really cool use of technology. Use your graphing calculator to find that value of m as described in Part C. And you might try this both on a calculator page and on a graph page. Part D is a very interesting problem. First, A of k represents that portion of the region S inside the circle described by r equal k times the cosine of theta. Now here's a graph to illustrate this situation. The circle is centered on the x-axis at k over 2, 0. As k increases, you can see that the circle gets closer and closer to enclosing all of the region S in quadrant 1. And that's the reasonable conclusion without any analytical justification. Now, I think you can also see this numerically. Here, I used the function nsolve to find the angle where the circle and the graph of r that defines S intersect for various values of k. Now the angles appear to be zeroing in on 1.571, or pi over 2. Now you might try to use your calculator to construct a larger table to see this limit more clearly. We need to find the limit as k goes to infinity of A of k. Now, from our graphical and numerical exploration, as k goes to infinity, the circle captures all of the region S in quadrant 1. So we need to find the area of S as theta varies from 0 to pi over 2. So using the TI-Nspire, I actually found an exact symbolic answer, and that's really cool. And here's the numerical approximation. And here's one more example for you to try. Consider this polar equation. First, try to sketch a complete graph of this polar curve. And then let S be the region enclosed by the graph of R in the first quadrant. Find the area of S. And finally, you know there's a line through the origin with positive slope m that divides the region S into two regions of equal areas. Find the value of m. I hope this video gives you a better idea of how to solve this free response question, and of how to use technology to solve, visualize, and confirm your results in at least some parts of the problem. This free response question presents some good opportunities to work with polar curves and area. And there are some nice conceptual ideas in here also. And just a reminder There are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.